And now in slide 060, we come to something which I really believe is beautiful, the butterfly wedge. The butterfly wedge, as you see there, and on the right with its spread tangential strings there, it looks like a butterfly. It comes from a bundle. You see in the middle a bundle of strings. And this idea of string here has nothing to do with string theory as far as I know. I just used strings to think about a different kind of wedge. It's good here to think of the context in which this butterfly emerged, and that is in thinking of an expanding web. It had already got to the point where the idea was that every atom in a toy physics universe has a spinal body that expands radially, and that radial expansion feeds the expansion of the tangential web. The simple Pythagorean wedge is useful for fluids. In the demonstration, we poured cat litter in, which is like a fluid. But in the case of an expanding web or expanding atom spinal body, taking in substance, a bundle of linear substance, and then spreading that out to fill the expanding space, the regular wedge just doesn't quite work for that. It doesn't work out. And so in trying to find something that did, this is what emerged, is a Pythagorean wedge. And it's really a pretty thing. The bundle of strings or bundle of material, it would actually be a substance, a very fine substance that is in a bundle. It enters in a radial manner and then spreads out. Half of it stays in that center spinal body, and half of it spreads out into those tangential wings. There are a couple of things to point out here. One is that we're demonstrating always with this basically one-dimensional thing, meaning that it's got just left and right as far as sensory dimensions. But as we know, in our universe, in the largest toy universe, there are 3 sensory dimensions. So there are really 3 toy universes with varying degrees of dimensionality. This one is a one-dimensional universe. Then there's a 2-dimensional, in which case there's 2 sensory dimensions, and then the 3 case. In each case, this still applies. What you're looking at here is just that the tangential material, which is really continuous, it's not individual strings, that tangential material spreads out throughout the entire space of sensory pointing dimensions. Another important thing to mention is that in developing the toy physics universes, the radial expansion is calibrated to the speed of light. So every increment, every turn of the crank where expansion occurs, the distance is taken to be that number c, which is our speed of light. Here in slide 65, we see that the beauty of the butterfly is enhanced by the fact that it partitions in the same way as the wedge. In the upper right corner, you see that we've selected a level that's like a level labeled v, and that's going to correspond to velocity in the special relativity story. So below that level v, that there are the black strings. So the point is, and it's really fascinating, that below that V, there is a butterfly, that black butterfly, and the remainder up at the top, after you've cut that off at that point, forms another butterfly. So just like the Pythagorean wedge partitions into smaller wedges, the Pythagorean butterfly also partitions into small butterflies, each of which could be partitioned further and further. The difference is that the butterfly has this property that it is fed radially by a bundle, and half of the fed material is retained by the center, that would be the spinal body of an atom, and half of it is redirected out into the outer expanse, the space of pointing sensory dimensions around the spinal body. Now, I want to point out here, it says we will recall this later. Look at that butterfly allocation equation. It's mass m times c squared. Recall c is the length of that bundle. So the overall wedge has that amount of material in it. M, a mass that is determined by the properties of that bundle, times c squared, which is that, like before, the c squared corresponds to the area of that wedge shape, that partitions into two smaller butterflies. One is the m times s squared, that really we think of as the yellow partition there, and the other is m times v squared, which is the black one. Later we'll bring this back up because we're going to find later that it matches extremely well with the space-time story of relativity. In slide 070, we take a little closer look at these two partitions. You see them again here in a little different arrangement. On the right, we see the golden or yellow partition. That one corresponds to web growth. The amount of material in there is m times s squared. That's that first partition. And it supports the growth of the web. So that extends out in all directions, the part that's tangential in all spatial directions. The lower partition, which is black, that corresponds to the amount of energy that sustains velocity. A really radically different concept of an atom in toy physics, and this comes straight from the geometry, is that basically an atom is self-propelled. This energy coming in from expansion, a portion of it, that black butterfly, is expelled out in the opposite direction of velocity. Now it's shown here as a butterfly, and later in the book, that energy is actually directed to support velocity. On the right-hand side of this diagram, you see the Lorentz contraction equation, and that is the relation between the original butterfly and the remainder that supports web growth. It contracts in the manner of the Lorentz contraction. The higher the velocity, the more that web growth contracts.